a person running, cars traveling down a road, a burning log, waves breaking on a beach. What do all of these things have in common? They are all examples of energy, and that energy, when it's traced back to its source, comes from the sun. As you watch this program, think about how do we get energy from the sun, and how can there be so many different forms of energy? Virtually all of the energy that warms the surface of Earth and sustains life on the planet comes from the sun. The sun radiates energy in the form of electromagnetic waves that travel to Earth at the speed of light. These waves have various lengths and frequencies that together make up the electromagnetic spectrum. At one end are high-energy gamma rays with very short wavelengths. And at the other end are radio waves with long wavelengths and lower energy. Close to the middle is a narrow band of waves called visible light that we see as different colors. Electromagnetic waves provide Earth with both heat and light. When the sun's energy reaches Earth, some is reflected off the clouds, some dissipates into the atmosphere, and some hits the ground where it's either reflected or absorbed. The energy that's absorbed turns to heat and is re-radiated back into the atmosphere. The energy now has longer wavelengths and lower energy. It is more easily absorbed by gases and warms the atmosphere. The warming of the Earth and the lower atmosphere, in part, is dependent on the type of surface the sun's rays strike. Fresh snow, for example, reflects most of the sun's radiation, and consequently very little is absorbed to be re-radiated. A blacktop road, on the other hand, absorbs much more radiation, and so emits a great deal of long-wave radiation. That's why blacktop roads are so hot in summer. The intensity of the sun also depends on the angle of the rays striking Earth's surface. When the sun is directly overhead at the equator, the rays are concentrated and hot. Near the poles, the rays strike the Earth at a more oblique angle. The same amount of sun's rays warms a much larger area of the surface of the Earth. This is the main reason why the temperatures are cooler in temperate and polar regions than in the tropics.
The sun and Earth both emit electromagnetic radiation. This movie will help you describe the differences between the types of radiation emitted by the sun and the Earth. Electromagnetic radiation is energy that travels in the form of electromagnetic waves. Different types of electromagnetic waves carry different amounts of energy. The shorter the wavelength, the more energy carried by the wave. The wavelength of emitted radiation is determined by the temperature of the object it comes from. The higher the temperature, the shorter the wavelength of emitted radiation. The sun, with its high surface temperature, emits a great deal of high-energy, short wavelength radiation. Energy emitted by the sun is also referred to as solar or shortwave radiation. Most of solar radiation is the visible light we see with our eyes, but it also includes wavelengths that we cannot see, like the ultraviolet light that causes sunburn. The Earth, however, being much cooler than the sun, emits lower energy, longer wavelength radiation. Energy emitted by the Earth is also referred to as terrestrial, which means land-based, or long-wave radiation. Although we cannot see long-wave radiation with our eyes, we detect it as heat. In summary, the types of radiation emitted by the sun and the Earth are determined by their temperatures. The sun, which is very hot, emits high-energy shortwave radiation, while the Earth, which is much cooler, emits lower-energy long-wave radiation.
Earth is constantly bombarded with enormous amount of radiations from the sun, which we receive in the form of light and heat energy. These radiations, in the form of visible, ultraviolet and infrared, have to first pass the Earth's atmosphere before reaching the surface. The ozone layer, which is present in the Earth's atmosphere, blocks some amount of harmful ultraviolet rays from reaching the surface. Of the remaining rays reaching the surface, part of it is absorbed by the Earth, and some, especially the infrared waves, are reflected back into the space. But some gases in the atmosphere traps this heat radiation and re-emits it to the surface, which leads to heating up of the environment. This exchange of incoming and outgoing radiation that warms the Earth is referred as the greenhouse effect. And the gases involved in this are called greenhouse gases, which mainly includes carbon dioxide, methane, water vapor, chlorofluorocarbons, etc. The greenhouse effect is essential in order to keep our planet warm. In the absence of this effect, the temperature of the Earth's surface would have been -20 to -40 degrees Celsius. But too much of something is bad, right? If the plants in the greenhouse receives excess heat, it would burn. And if we consider planet Earth, over the last 2 centuries, human activities have changed the Earth's atmosphere in a dramatic way. The amount of greenhouse gases have increased and are still increasing. They trap too much heat. And this excess of greenhouse effect results in global warming, which is an increase in the Earth's average temperature.
We humans are changing global climate. Concentrations of greenhouse gases in the atmosphere are at their highest levels in more than 200,000 years. If the trend does not change, scientists expect the seas to rise 2 feet or more over the next century. Island chains such as the Maldives will disappear from the map unless we reverse the predictions. Thank you very much.
I became very interested in the Maldives for one simple reason, because here you can study sea level changes and the various factors which interacts to change sea level in a way which you can do in no other place on the globe. The IPCC report had a chapter on sea level changes. In their writing, they say that low-lying areas like the Maldives, specifying the Maldives, will be subjected to a future flooding. And they will disappear from the surface of the earth within 50 years or at the most 100 years. These were, so to say, the baggage I came with. And then we began our research, not knowing what I would going to find. The first thing I found was a tree in the Viligili. And then I heard from the people that this tree had been staying there in the same position for at least 50 years. This is quite a remarkable tree, because it has been in this terrible situation right out on the beach, and any little change in sea level would have wiped it out. And with this position right on the beach, totally, any minute, so to say, it could fall over a big wave, and it hasn't done that for 50 years. That tells us a very important fact. Sea level cannot be in the rising mode. It can be stable or it could be a falling mode, but certainly not in the rising mode, because then it would have wiped out that. And that is the message of the tree.
Niels Axel Mørne is on his way to the tiny island of Losfushi with Musa Manik of EcoCare in the Maldives. They're carrying a piece of the skull of a skeleton that appeared from the coral reef there a few years ago. On the evidence of where the skeleton was found, and from carbon-14 dating, the sea level at the time the woman lived may now be reliably ascertained.
Now we are coming out on this beach rock, a beach cemented into a hard rock. And outside there we see rock sticking out, and that's the place where you found
the woman.
The woman. We go around and see it. That's a good idea.
Go that way and then,
that's a good idea. The reef woman was embedded in a beach sand at about same sea level as today's sea level. And that was 1,200 years ago. That's the ribs, yeah. And here is the skull. So this one should have come here, I think.
right.
And because she has a very delicate cranium, we can be sure that it's a woman. So you were completely correct. Because of its position in the reef, we can see that she lies embedded in a shore sand. And that shore sand is then covered by a cemented coral rubble, which tells us other things, that subsequently to that level, 1,200 years ago, sea level rose, brought this rubble together and cemented it, then fell back in a couple of steps. And those steps are quite remarkable. In the last 200 years, sea level has been about 30 centimeters higher than today. At about 1970, something remarkable happened. Sea level fell down to its present position. That fall in sea level, which no one had expected to see, we can see all over the Maldives. It's very well recorded and established. And that, of course, gives us a completely different story than it's generally given. Here we are at the top of the present-day wave action. They deposit these coral fragments, and they are white because they are rounded by the waves of today. The other level, the gray level, is the top of the waves at the previous time. So that means a difference in height means evidence, real evidence that sea level has gone down. It has not gone up.
So the sea level around the Maldives is not rising. On the contrary, there has been a remarkable fall of 20 to 30 centimetres in the last 30 years. The conclusion of Nicholas Mørne's observations may be that archipelagos like the Maldives will not be inundated after all.
I think The reason for this fall in sea level about 1970-75 is a strongly increased evaporation. The Indian Ocean is very warm and the evaporation is exceptionally strong. And that strong evaporation has made the sea level in this region to be exceptionally low. So it's 30-40 centimeters lower than gravity tells it that it should be. And that's quite remarkable. I mean, it's going up so much water vapor that it has not time to fill. Those things were, for me, exceptionally interesting variables to study.
Evaporation from the oceans may actually ward off any future rises in sea level. Evaporation from the tropical oceans to the atmosphere moves the enormous volumes of water to other locations like the poles, where it falls as snow.
A rise in evaporation is a cause of becoming, that it becomes warmer somewhere. That's interesting. And it means if it gets more evaporation here over the Indian Ocean, somewhere else it can get more precipitation. But you cannot have increased precipitation somewhere if you don't have increased evaporation somewhere else. And that is the balance of the globe.
Being blamed for playing a role in the creation of GWPF. It's one of the better things I get blamed for, but anyway. What I'd like to talk about today is something rather dear to my heart, but obscure to everyone else, which is the narrative of global warming. It is a narrative that we've approached defensively, but which I think is intrinsically implausible, if not absurd. At any rate, the question is, how does this come to be? And it seems to me part of the reason is how little science permeates normal discourse. Over a half century ago, C.P. Snow, some of you might remember the name, he's a novelist, English chemist and physicist, served in the civil service and even briefly in the government, World War II. He examined the implications of what he referred to as two cultures. And I'll quote from him briefly. "A good many times I've been present at gatherings of people who by the standards of the traditional culture are thought highly educated and who have, with considerable gusto, been expressing their incredulity at the illiteracy of scientists. Once or twice I've been provoked and have asked the company how many of them could describe the second law of thermodynamics. The response was cold. It was also negative. Yet I was asking something which is the scientific equivalent of, have you read Shakespeare? I now believe that if I had asked an even simpler question, such as, what do you mean by mass or acceleration? Which is the scientific equivalent of saying, can you read? Not more than 1 in 10 of the highly educated would have felt that I was speaking the same language. So the great edifice of modern physics goes up, and the majority of the cleverest people in the Western world have about as much insight into it as their Neolithic ancestors would have had. Trouble is, I don't think a lot has changed in the 60 years since C.P. Snow made this assessment. And although maybe it's extreme, some would, I suppose, say that ignorance of physics might not impact political ability, but it almost certainly impacts the ability of non-scientific politicians to deal with nominally science-based issues. Moreover, the gap in understanding is also an invitation to malicious exploitation. certainly seen that. Given the democratic necessity for non-scientists to take positions on scientific problems, belief and faith inevitably replace understanding, though trivially oversimplified false narratives serve to reassure the non-scientist that they are not totally without scientific understanding. The issue of global warming, unfortunately, offers numerous examples of this.